Hello, everybody. Welcome back to MI7397 Business Intelligence / Predictive Analytics. This is week 8, video 2, under the emergency situation of coronavirus. I hope everybody is doing well, is staying healthy and hygiene, and let's continue with this week's content. So here I'm going to briefly talk about neural networks to get the chapter of neural networks started, and I'll talk about neural networks at the high level, at the conceptual level. I'll talk about its structure. I'll talk about some of the key concepts. I'll introduce a video to you. It is probably the best video at an introductory level to talk about the inner workings of neural networks. Why does it work in why does neural network have the ability to see the correlations, associations between the input and target data, target variable, see the correlations between them that the human eyes can't see? How does it crack the numbers and extract the useful patterns from the data? So I'm going to talk about that briefly today. I will not do any hands-on demo here today because this is the first part of talking about neural network. I will have a second video talk about neural networks, and that's going to be in week 9's, the adjusted week 9's content. Week 9 is going to be have the first exam, the midterm exam, and also for that same week, you're going to study the rest of neural networks and also complete homework 6. Okay, let's get started. Here you can see that I have the slides turned on, so I hope you will follow along with this video with your note taking and with your slides open as well. So neural network can be used for classification as well as for prediction purposes. It is a supervised model, and it does have a target variable. It tries to find the link between the input variable that you provide to the network and the target variable, and try to find the association between these variables with the target variable in the observations that you feed into the model, and tries to capture the big patterns that may hint at what information might be predictive in terms of the target values. It is so far in this semester and in this course the most complex model, and the complexity is not only because of the computations that go into calculating and deriving the solutions. And let me tell you, there isn't a single solution here. So, and not in the sense that you might have alternative trees, and you can prune the tree to have different results of the model. And in some sense, that's equivalent, but in another sense, that even if you have the same structure, even if you have a tree with the same structure set up with the model training, and it trains over time, it literally does not stop. It keeps training and training and training, and get to a model that crunches more and more and more data, or crunches the number in a finer and finer way, so that it reduces the errors. Ultimately, the errors are never reduced to minimal. The error between prediction and the data is going to be reduced. It will keep being reduced and shrinked over time when you train the neural network but it will be long, maybe days even for a simple model, and a somewhat small data set of maybe 3,000 or 4,000 observations, similar to the data set that we use here for the course. Even with such a somewhat small data set, the model can keep training for days and it won't converge. It doesn't mean that the model is deficient, but it simply is because that there are so much variances in the data that the model can learn, and at some point that the model is going to overfit with the data. So it will be far before the model soak up everything from the data that the model will be optimal. I'll talk about that in a few minutes. So it's a complex model, and it does have a lot of concepts to learn about how the neural network model work. And I'm only talking about fairly simple structured a neural network that has a small number of layers and neurons, and the architecture of the simpler versions of the neural network model I'm talking about is the fully connected multi-perceptron for propagation models. Has a combination of connected links and nodes and links that work somewhat like regression models. If you take them apart, every node accepts input from the previous layer, and it forward feeds into every node in the subsequent and downstream layer, and every node works somewhat like a regression model, that it uses a linear combination of the inputs from the previous layer, and it does a nonlinear transformation, somewhat like a logistic regression, which also does the nonlinear transformation and translates into a value that's in the small range, understood as probabilities in the neural network terms, and it further propagates to downstream layers until it hits the output layer. So the quickest way to describe the units of the neural networks is like a bunch of regressions. For the simpler version of the neural network model that we focus on here, it's called Multilayered Perceptron. Forward feeding network that has 3 distinct types of layers. It has input layer, has hidden layer or layers, and output layer. And other than the input layer, all the other layers, including the hidden layer and the output layer, has hidden neurons. We call neurons, and the input layer are not. Input layer has neurons that are not hidden, but the input data neurons. Every variable is a neuron, but observed neuron, and the connections are how the data or information is fed from upstream layers to downstream layers. So here is a typical multi-layer perceptron forward-feeding fully connected neural network. You have in this example here, there are 2 layers, hidden layers in the middle. Let me get the laser pen here. Okay, so these would be the hidden layer areas, and for this example, it shows 2 hidden layers. But you can, by the same logic, you can have 3 layers. You could have only 1 layer, you know, as many layers as you desire. This is the input layer. And this is the input layer. Each node here represents a feature or variable, equivalent terms to describe input data. And altogether, the input layer will include the entire training data set. So, you know, if you have 10 input variables, you would typically have 10 nodes in the input layer. Each of the node in the hidden layers or layer is a hidden neuron, and these hidden neurons are hidden, and it's quite conceptual. It's not perceptual. They are hidden. They are unobserved, although you can calculate it, but it changes. So that's why they are called hidden. But you can still specify the number of hidden neurons in each of these layers, and you can also specify the number of layers, at least 1 layer in the hidden layers. The output layer consists the output neuron that would translate directly into an output prediction. So let's say if the target variable is a binary variable, this output layer will output will predict the probability that the target variable will be take the value of 1, and if that probability is greater than 0.5, then the probability is greater than 50%. It's more than 50% of chance that the target variable will be 1, so the prediction will become 1. So let me take a note here. So here, typically, if it's a binary classification problem, if the target is binary, then the prediction will be 1 or 0, but the output layer will first calculate a probability it will be between 0 and 1. I'm sorry for that. 0 and 1. So, and the probability will take 1 if probability is greater or equal than 0.5. So, the output layer will first calculate the probability, and based on the probability, based on the cutoff value, prediction would be either 0 or 1. Excuse the boy over there. Probably there's a family fight there between the brothers and sisters, but it's none of my business, and it's none of your business. So, and let's stay focused here. Okay. But the what if it's not binary classification, but multiple multi-category predictions? Then it will output as many number of output neurons as there are a number of discrete labels in the target variable. Say if you're predicting whether or not the outcome is one of 3 different possibilities, then you will have 3 different neurons here, each representing one of the label, and the model will output probability that the target variable will take each of the one of the three classes, and then the class with the highest probability will become the predicted label here. So this is called the topology of the neural network model. You would describe what are the three layers: the input, the hidden, and the output layer, and what is the number, or what is the number of actual layers in that component, and what is the number of neurons in that particular layer. So for here, the input layer has 6 input neurons. The hidden layers actually have 2 hidden layers. The first hidden layer has 4. Excuse me, let me clear that. The first hidden layer has 4 hidden neuron, and the second hidden layer has 3 hidden neurons, and the output layer currently has 1 neuron. Okay, that's the topology. Model training. The connections between, let me go to here. The connections, each of the lines here is a connection, and so on and so on. Is the pathway where information or variance of the training data is input through, is transferred through the layers from one node to another, to the downstream layers, and the calculation is feed forward into the downstream layers. Each of the connection represents a coefficient. It's fairly similar to a regression model, where take this hidden neuron. It takes input from 6 of the input neurons, and each of the input neuron is multiplied by the coefficient that represents the connection here, and after the linear combination of the 6 input neurons with the 6 slope coefficients, and after some activation function transformation, it becomes the value of the first hidden neuron of the first hidden layer. So here each of the connection represents the slope coefficient, or the weight estimate, or weight coefficient of the connection. So the information goes from left to right. It goes through a forward propagation, where the information is flowed through them, and you get a bunch of coefficients, many coefficients here. Each of the line represents a coefficient. You also have a lot of the beta bias coefficients, and some other coefficients. Together, these coefficients, and with the input data x, it together calculates the prediction for the output. Obviously, at the first few rounds of training, these coefficients are not going to be optimized, so the prediction will be far off, and that's then the error is calculated, and it goes through one round of backward propagation to figure out how to modify these coefficients, because the data will not be modified. Data are given or fixed. Only the coefficients are being optimized, and it goes through one round to adjust the coefficients to try to make to improve the accuracy of the model, and it goes on and on and on, iteratively goes through these loops, many times in order to optimize the coefficients of the model, while keeping the entire structure of the topology of the neural network fixed. So the backprop, feeds the weights of the errors through the different components of the model in trying to figure out how to adjust the beta coefficients and the B. These doesn't mean the lines are this line. It doesn't mean this line is beta and this line is B, but collectively you have these coefficients that represents the connections and links, and through the back propagation, their exact values, their estimates are being adjusted in order to increase the accuracy of the model. Neural networks get their name because computer scientists who work on machine learning and specifically invented the neural networks were trying really hard to try to make computers work similarly as humans, because in those ages computers are trying to do as well as humans can do. In those years computers are not as good in terms of performing tasks that humans can do well. Computers are certainly very fast from the beginning. They can calculate they have big memories, they have fast computation speed. However, they cannot do very complex things. They cannot learn very complex skills as humans can do very efficiently. So they try to make the computer imitate what humans can do. The reason why neural networks have that structure is because human neurons, based on biology, it does look similar like that, and the nerves will collect information, will feed back into the nerves, feed back into the central neural system to process the information and feed back to take actions, to react to the world. So neural networks does have a similar structure. The reason that the nodes are called nodes is also because of these terminologies in neuroscience and biology. This describes the two process of forward feed. You have the linear combination. Linear combination, it calculates a sigma, and through an activation function, it translates into a value of y that is very small, that imitates probability terms. And later you'll see a video that explains these terms in through visual cues. It will become much more intuitive. Neural networks can solve classification problems. It can also make predictions about target variables that's interval or continuous variables. So neural networks are very versatile in terms of solving problems. Although the downside of neural network is because it's so complex, the numbers of the hidden neurons and the connections, they change, and there are so many of them, it becomes untractable. Therefore, although the results are beautiful, you have prediction results, you have accuracy margins that are smaller than 1% of that's far better than human errors. But if you dare to try to explain how the neural networks are making prediction decisions, you are faced with an unbeatable mountain. It's really hard to crack open what is happening inside the neural networks. So that's why it says it's opaque. It's a black box. Neural network is like a black box, and that's why scientists and researchers are trying to push really hard for this explainable AI, in trying to invent techniques that can crack open what's inside a workable neural network model that is proven to be making highly accurate predictions, but hard to know what's inside of it. Explainable AI is trying to solve those problems. Model is quite complex. You can keep adding the layers, and also you can keep expanding the number of hidden units. You can put as much as 500, not in SAS, but in other computer package. You can put in as many as 500 hidden neurons. You can put 5 or 6 hidden layers. It becomes very, very complex. You can also train the network for multiple rounds. It will make the model more accurate in predicting the values in the training data set. It does become overfitting fairly quickly. A number of layers add to the complexity of the model, as well as the number of hidden units in each of the layers. And the number of input variable spaces also increase the complexity of the model. Model selection then becomes a problem. When you have a powerful model that is able to soak up all the nuances and variances of the data, when is the optimal time that you make the model to stop? You don't actually stop a model, but you do need to make sure that you do well in selecting a model that is not overfitting, but that performs well enough in the training process. Model selection criteria based on the validation data set. Make sure. So far in the semester, I've always emphasized that when you train the model, you rely on the training set error rate in order to keep pushing the model. But when you compare and try to select the best model, you make use of the error rate or error metric. It can be a misclassification rate. It can be mean square or average square average squared error of the validation data set to try to select the best model. Here, the selection of the criteria depends on the kind of task that you're performing. If it's a classification problem, misclassification rate will be perhaps the best choice. But if the prediction is about an interval variable, then the mean square error, this is misclassification error, and average square average square error is the error for selecting a best model for the target variable of an interval variable. Profit loss involves the decision weights and decision making, which is adding one more layer of complexity here. We'll talk about decision weights in the model evaluation week. The input variables do need to be normalized or standardized in order for the model to perform stably. And although there are two ways to standardize the data, there is a z-score standardization or a min-max standardization. The min-max would be preferred here for reasons that will become clear when I introduce the video, and that you guys watch the video. You'll see that the values of the values inside the neural network after each activation function, it is capped in 0 and 1. So that's why the input variable better be kept between 0 and 1. That's when the min-max standardization becomes very useful. To deal with a skewed distribution, as I talked about in the first video, you will make use of the log transformation, but it's not always required, and it's not always even optimal to do that. So one of my suggestions would be to when you have skewed input variables, you should try both approaches. One is apply transformation and use logarithm transformation to fix the skewed distribution of those variables, and apply the same model, and also you on the side you do another version of the model training while you keep the original distribution of the skewed variable, and you compare the model, because the only thing that's different is the input variable logarithm transformation. You can empirically see which approach is better for your specific case. The necessity to, or the benefits of taking log transformation machine learning does depend on each case specifically. So there's no universal rule or universal guidance to be provided here. If there are erroneous values, imputation or replace imputation would be a better term to say, to impute the missing values that are as a result of the erroneous values. You'll replace, and I suppose replace is good, but it does mean that you first replace the erroneous values with 0, and then you will impute the 0 values because of the erroneous values with imputation methods. Missing values impute, interval variables use log transformation. There is, as I said, there is caveats. I just talked about this, and with categorical variables, because their labels are meaningless. Let's say gender is a special case of categorical variable. It's a binary variable that has only 2 labels, male and female. Labels do not take values, so you can assign 0, 1 flag values to them. Typically you would have k minus 1 number of labels. K is a number of discrete labels. If there are only 2 discrete labels, you will only create 1 indicator variable. In the case of gender, k equal 2, you'll have k minus 1 is 1 dummy variable to indicate whether the case is a male or a female. And you can name that variable specifically using the gender of the label that you assign, value of 1. For instance, if the case not fail, I'm sorry. If the case is female, and you assign female of label 1, the variable will take 1. If the case is male, instead, and the variable will take value of 0, indicating that this observation is not a female but a male. Okay. Now it's time for me to introduce the video. This video is already uploaded to Blackboard. It's in a useful video page, and the way to get to that video is explained here about this arrow. So in the video, I would like you to specifically focus on these terms. At 2 minutes 25 seconds, about for 1 minute or so, it will talk about what is gradient descent. Gradient descent is the backbone of the optimization process of neural network in trying to back propagate the errors and try to improve and optimize the coefficients of the neural network. You know, those coefficients that I mentioned, those betas and those b's. It's a collection of coefficients. Gradient descent gives the model the power, gives computer the power to improve them bit by bit, iteration by iteration, in getting the model closer to the ground truth. Although this is confined by the ability of the training data set, and with the caveat that there is noise in the training data. And after you have learned about gradient descent, what it means, it will talk about neural network at a higher level picture, and then it will talk about several things specifically. First thing it talks about is minimizing error. How does it specifically do with gradient descent in minimize or reduce the error and adjust the coefficients? And after you have a better version of coefficients with the input data, how does it forward propagate the information through the layers? And what does it mean by probability and activation functions? And after that, after activation, you have a neuron, and information will keep fed forward, layer through layer, a neuron through a neuron. But what does each of the neuron mean? And also, another myth here is that neural network is probably one of the best nonlinear model that can figure out nonlinear relationships. But all of the unit, sort of the smaller components of the neural network can be seen as mini regression models. But the regression models are quite linear. Even logistic regression, there's only one step that transforms the linear to nonlinear. How so is it possible? How is it likely that neural network models can perform nonlinear predictions so well by using a bunch of linear models? So at this part of the video, it will talk about how it leverages each of the neurons to put things together and make excellent predictions. And so it will finish off by putting everything together and give you some examples. I hope that you will make very good use of this video. Every student that watches the video, give me feedback that this video is so helpful. Together with reading the book, it helps it will help you get a deeper understanding of what neural network, or a more lively understanding of how neural networks work and how does it do well. But however, do read the book and understand those basic concepts, and try to go through, follow the book and go through how does forward feeding and backward propagation works by using a few of the example numbers inside the textbook. It does a very good job in illustrating through text how the information is transferred inside the neural network, and that's only after you have read the book and be familiar with those concepts, and then you look at the video here, then you will be able to understand, in a higher picture, how does it do, and how do all the components put together. All right, this will conclude the first part of the neural network lecture. I hope you enjoyed this video. I'll see you soon. Bye bye.